In this problem, we're given a formula for the number of times a new pop song has been downloaded, T weeks after its initial release. And in part A, it asks us to find after how many weeks is the rate of change of the number of downloads maximized. So I want to maximize the rate of change. Of the number of downloads. So, if I need to maximize the rate of change, I'm going to maximize the first derivative. And to do that, I'm going to find the second derivative, set it equal to 0, solve for x. Okay, so that's my plan. So I've started by writing out the original function, and I wrote it a little bit differently so that I can use the power rule to find the derivative. So I have to find the first derivative before I can find the second derivative. So I have -1 times the 3.3 million and that's times 1 plus 500 e to the negative 0.45t, and now that's going to be to the -2 power according to the power rule. But I have to multiply by the derivative of the inside, which is 500 e to the negative 0.45t times the derivative of the exponent, which is negative 0.45. Okay, so now I'm going to take negative 3.3 million times 500 times a negative 0.45 and multiply those together. And I get 742,500,000. And then this is going to be times 1 plus 500 e to the negative 0.45t to the -2 times the e to the negative 0.45t. And then I can take this part, which is to a negative power, move it to the denominator. And I have my first derivative. Oops, it's not -2 anymore, just 2. Okay, so now I'm going to take my first derivative over to a fresh page, and I'm going to find the second derivative. Okay, so here's my first derivative, and now I can find the second derivative by taking, remember the formula is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, and that's all over the denominator squared. So this starts out as the denominator times the derivative of the numerator. So that's going to be 742,500,000 e to the negative 0.45t times the derivative of the exponent, which is negative 0.45. And that is denominator times the derivative of the numerator. Then we're going to subtract the numerator, 742,500,000 times, kind of running out of room, so I got to continue down here, e to the negative 0.45t, and then we're going to multiply by the derivative of the denominator, and that's 2 times 1 plus 500 e to the negative 0.45t, and that's to the 1 power, times the derivative of the inside. Derivative of 1 is 0, so we have the derivative of 500 e to the negative 0.45t is going to be 500 e to the negative 0.45t times the derivative of the exponent, which is negative 0.45. Okay, so this and this, all the way to there, that's the second part. And it's all over the denominator squared. So this is going to be to the fourth because it was to the second power, and then we square that and we get the fourth power. Okay, this is a little lengthy. So what I'm going to do is I'm going to look at what can I factor, what's in common. All right, so in the numerator, I have 742,500,000, and I have that in the second part as well. And I have a negative 0.45, and I have that there as well. And what else is in common? E to the negative 0.45t, e to the negative 0.45t. And I have 1 plus 500 e to the negative 0.45t. I have two of them here, so I'm going to bring that down to 1. Okay. So now, what does that mean? We've got 742,500,000 times the negative 0.45 times e to the negative 0.45t times 1 plus 500 e to the negative 0.45t. And that was everything we had in common. So that's going to leave me with 1 plus 500 e to the negative 0.45t. That's the only thing that's left in the first set of brackets. In the second set of brackets, so I'm going to minus, what do I have left here? I have 2 times 500 e to the negative 0.45t. Cha-ching. Okay. And this is all over 1 plus 500 e to the negative 0.45t, and that's all to the fourth power. All right. Now, next thing I'm going to do, I'm not done simplifying yet, but let's take a look at what we have and what we're going to do. I'm going to set this whole thing equal to 0. So what can I ignore? I can ignore the denominator. That doesn't do anything, setting this fraction equal to 0. The 700 million thing can go, because I could divide both sides by that, and 0 divided by 700 million, still 0. This constant can go. E to a power cannot equal 0. So that's out. Okay. So I have 1 plus 500 e to the negative 0.45t, and I have 1 plus 500 e to the negative 0.45t minus 2 times 500, so that's minus 1,000 e to the negative 0.45t. And so let's simplify those on the next page and set that equal to 0. Okay, so I have 1 plus 500 e to the negative 0.45t times 1 minus 500 e to the negative 0.45t equals 0. And I can solve those individually. Okay, so here we're going to have 1 equals negative 500 e to the negative 0.45t. Divide, and we get negative 1 over 500 equals e to the negative 0.45t. So when I go to take the natural log of both sides, now I'm taking the natural log of a negative. Not cool. Can't do it. So this one is out. All right. That was actually nice. So now, what if I have 1 equals 500 e to the negative 0.45t? So I have 1 over 500 equals e to the negative 0.45t. Take the natural log of both sides, and I get the natural log of 1 over 500 is equal to negative 0.45t. So I can divide both sides by negative 0.45. And t equals something. Okay, so here we get 13.81. So that is the value that is going to maximize the rate of change of the number of downloads. Okay, so now let's go back to the original question. So this is going to happen after 13.81 weeks. And then in part B, we want to find the rate of change of the number of downloads found in part A. So I'm going to find f prime of 13.81. And that's just calculated by plugging into the formula for f prime of t. So you're going to take the 742,500,000 times e to the negative 0.45 times 13.81 and put that all over 1 plus 500 e to the negative 0.45 times 13.81. And then we're going to square that. And I get 371,249. And then in C, you want to take that 13.81 and plug it into the original function and evaluate that. And so that's how you do that problem. I'm going to let you do the last bit on your own.